Chaos theory spans over many areas of mathematics and describes how minor alterations to the initial state of a system can have significant consequences. The focus of this video is the chaotic behaviors that linear systems and linear equations can display. Consider an equation where x is equal to the previous iteration of x multiplied by a coefficient plus a constant. Now, if we take the first and second iterations of this equation and substitute the first equation into the second, we get a version of the equation which gives us the value of the second iteration of x based on the first iteration, x0. This process of substitution can be applied to any iteration, each time multiplying by 3 and adding 2. With this, a general equation can be created where n represents any real number. If we expand the brackets of the equation, we can separate the equation into two parts, one being 3 to the power of the current iteration multiplied by the initial state, the other being a geometric series which can be rearranged into an explicit equation for simplicity. We now have an equation for any iteration of x, with which we can calculate how minute alterations to the initial state will affect the final state. By adding 1/1000th to the initial state, the value of the 10th iteration changes by roughly 59. Subtracting the equations from one another gives the difference caused by our minute alteration for any coefficient. According to this, any equation with a coefficient of 1 or less will not display chaotic behavior, as the difference will be multiplied by either 1 or an increasingly small number. Chaotic behaviors can also be displayed by systems of linear equations. Consider this system of linear equations. First, the system is converted into matrices and vectors. We can take the first few iterations of this system and substitute them into each other. This process works for any iteration of the equation, allowing us to create a general equation. Expanding the brackets gives an equation consisting of the coefficient matrix to the power of the iteration multiplied by the initial values, in addition to a geometric series, which is once again simplified to an explicit equation. With this general equation for any iteration of the two unknowns, we can consider a near identical system of the same iteration with initial values that have been slightly altered. By subtracting the equations from one another, the value of the difference caused by the minute alterations can be calculated. For example, in just 10 iterations, changes of 25,000th and 33,000th have caused differences of over 3,000. This chaotic behavior is due to the coefficient matrix having one or more eigenvalues higher than 1. For the coefficient matrix's eigenvalues are 1 or less, the difference would be multiplied by an increasingly small coefficient. To conclude, linear equations and systems of linear equations whose values depend on previous iterations of themselves will exhibit chaotic behavior if their coefficients are greater than 1. I hope you found this brief overview of chaos theory in the context of linear algebra useful.